Hello everyone, QED Math over here, and today we're going to be reviewing the 2005 HMMT Algebra round. So here's the first question. How many real numbers x are solutions to the following equation? So we have x equals 1, x equals 2, and x equals 3 being critical points. Thus, let's divide into appropriate cases. So case 1, I guess I'll decrease this. So case 1, x is greater than or equal to 3. In this case, we have x minus 1 is x minus 2 plus x minus 3. So x minus 1 is 2x minus 5. So x is equal to 4, and x equals 4 is indeed in this appropriate range. Case 2, so 2 is less than or equal to x, less than 3. So x minus 1 is negative. X minus 1 is positive. X minus 2 is now non and negative, so absolute value will change to 2 minus x. And then absolute value will still be x minus 2, but now x minus 3 is now non-negative. So this becomes 3 minus x in this case. So we have x minus 1 is equal to 1. X equals 2, so x equals 2 is also a solution. Case 3 is when 1 is less than or equal to x is less than 2. In this case, we have x minus 1. Now the rest is now non-negative, 2 minus x plus 3 minus x. So we have x minus 1 is equal to 5 minus 2x. So x is equal to 2. X equals 2 is not in this range. And then finally, the last case is case 4 is when x is less than 1. And if x is less than 1, everything there is negative. So 1 minus x is equal to 2 minus x plus 3 minus x. 1 minus x is equal to 5 minus 2x. So x equals 4, not in this range. X equals 4, not in this range. So in fact, we've actually repeated solutions, and x equals 4 and x equals 2 are only real solutions. So we have 2 real solutions. Next problem. How many real numbers x are there to the following equation? Let's divide by 2005 raised to the power of x. This gives us this. Now the thing is, 2003 over 2005 and 2004 over 2005 are all smaller than 1. So when we raise it to a power of x, we're actually going to have a decreasing function. So if this is a decreasing function, it's going to hit the y equals 1 at exactly 1 point. So there's only one real value of x. Next, let x, y, z be distinct numbers such that the sum is 0. What is the maximum possible value of this? So what we have to do is we have to note that x squared plus y squared plus y squared plus z squared is equal to x plus y plus z squared minus 2xy plus xz plus yz. X plus y plus z is 0, so this is just negative 2xy plus xz plus yz. And now substituting this in, we'll get, this is fixed at negative 1/2 for all x, y, and z, no matter the value of x, y, z, such that x plus y plus z is equal to 0 and x, y, z are distinct. Okay, next problem. If a, b, and c are greater than 0, find the smallest possible value of this. So let me set up the inequalities. Floor of a plus b over c will always be less than or equal to a plus b over c, which will be less than the floor of a plus b over c plus 1. And a similar thing for the rest. This is just the definition of the floor function. This is just using the definition of the floor function. So now let us see. So you want the smallest possible value of this expression. So smallest possible value of the expression would, if we label these columns 1, this column 2, and this column 3, we can kind of get the smallest possible value. We can get a bound on it by basically adding everything in column 2 and everything in column 3 and expressing that as an inequality. So let's just do that. A plus b over c minus 1 plus b plus c over a minus 1. That's a really big one. Plus 1 minus c plus a over b minus 1 is I'm subtracting 1 from columns 2 and 3 and adding them together. is less than or equal to 4a plus b over c plus 4b plus c over a plus 4a plus c over b. Now here's something very cool. What we can do is we can rewrite the LHS as this. 4b over c plus c over b plus 4 a over b, b over a. And then less than, I'm gonna just call this our x, or the desired expression. So now look at this. All of these expressions are going to be greater than or equal to 2. We can conclude this since a, b, and c are all positive, and this is just a consequence of the AMGM inequality. So therefore, this expression is always going to be greater than or equal to 2 plus 2 plus 2 minus 3, which is 3. So in other words, x must be greater than 3, in other words, and then we want the minimum possible value of x, so since x is going to be an integer, since it's comprised of 4 functions, the minimum possible value attainable is 4. Okay, the next question. 10 positive integers are arranged around a circle. Each number is one more than the greatest common divisor of its 2 neighbors. What is the sum of the 10 numbers? So the circle, A1, A2, A3, A4, A5, A6, A7, A8, A9, A10. So without loss of generality, let's assume A1 is the maximum value. We can do this since a circle, we can just rotate our numbers. So now let's apply the definition to the pair the triple A10, A1, A2. We know that each A1 will be the GCD of A2, A10 plus 1, or in other words, this is the case. Okay, sorry, plus 1 is not here anymore. Okay, so now we need to note that since A1 is the maximum value, A2 and A10 will be less than or equal to A1. So in this case, since they're less than or equal to A1 and the GCD is A1 minus 1, we must have that A2 is equal to A10 is equal to A1 minus 1. So now let's replace this with A1. That's the only way to ensure that kind of GCD. So now we have, this is our new circle. So now let's apply the exact same definition to maybe the triplet A1, A1 minus 1, and A3. We'd have A1 minus 1 is equal to the GCD of A1, A3 plus 1. In other words, GCD of A1, A3 is equal to A1 minus 2. So since A1 minus 2 is the GCD, it's also a common divisor. Therefore, we must have A1 minus 2 divides A1, or not or, it's an and. A1 minus 2 divides A3. Call this equation 1, call this equation 2. Equation divisibility condition 2 is not really that useful, so let's move on to divisibility condition 1. So we know that A1 minus 2 must divide A1. So this actually restricts the number of possible values of A1. So the implication is that this is an integer, which means that this is an integer, which means that this is an integer, which means that this must be true. Well, divisors must be a divisor, so 1, 2, which means A1 is either 3 or 4. So now let's just construct the values. So if A1 is 3 by construction, this must be 2. And we know it's symmetric, so let's just do the right side and then copy it over to the left side. So this is the dot, the GCD of 3 in the dot plus 1 must be 2. So GCD of 3 dot must be 1. Therefore, the dot must be 2. The reason why any dot cannot be 1 is because if we were to have this equal 1, and if we were to do GCD of 2 dot plus 1 is equal to 1, this implies that the GCD of dot and 2 is 0, which is a contradiction. So every AI in the circle must be greater than 1. So coming back to this, we saw that the dot must be 2, right? It cannot be anything greater than 3 for the reason that 3 is the maximum value by construction. Next, let's look at this circle. So that means GCD of dot comma 2 must be 1. So that means the dot must be 3. Now, if we look at this, the GCD of dot comma 2 is 3. And the GCD of dot comma 2 is 2. So that means this must be 2. Now let me just copy over what I have, 2, 3, 2. And now look, I have 3, 4, 5, 6, 7. I have 9 values. Only thing remaining is this. So GCD of dot comma 3 has to be 1, meaning that the dot has to be 2. But if dot is 2, that means this is a contradiction. Because GCD of 2 comma 2 is 2, add 1 to get 3, and 3 is not 2. So A1 equals 3 is out of the question. Therefore, there must be a valid construction with A1 equals 4. So if we do 4, 3, 3, and this is the dot, GCD of 4 comma dot must be 2. So that means the dot must be 2. The GCD of dot comma 3 now must be 1, meaning the dot must be 2. It could be 4. It could be 2 or 4. I'll leave 4 as a homework exercise. So if the dot is 2, so now we have here GCD of 2 comma dot is equal to 2. So that means the dot must be 3. Now I'll copy this over. 2, 2, 3, right? 2, 2, 2, 3. I have 4, 5, 6, 7, 8, 9. This is the last number remaining. GCD of 2 comma dot must be 2. So dot can either be 2 or 4. We see that dot equals 4 works. So this is a valid configuration. By the problem, it seems that this is unique. Again, I want you to check when this one, I believe, was 4. So, but this is the valid configuration. Now when we sum it, what I do is divide this up, do this times 2 and add the 8. So 2 plus 2 plus 3 plus 3 is 10, times 2 is 20, add the 8, 28. Okay, question 6. So find the sum of the x-coordinates of the distinct points of these two graphs, of intersection of these two graphs. So basically, in problems like this, where it seems like you'll get an ugly quartic, we usually want to look for symmetry. But if you try to look around, we don't see any symmetry. So let's just try to get the quartic. At most, it'll probably take like 2 minutes of algebra. And let's just see if it works. So x squared is equal to x plus y plus 4 would imply that y is equal to x squared minus x minus 4. And plugging in this in gives us x squared minus x minus 4 squared is x squared minus x minus 4 minus 15x plus 36. Now, if we expand this out, x squared gives us x to the fourth minus 2x cubed, 8, 9x minus 7x squared, 8x, 16, x squared, 16x, 32, x to the fourth, 2x cubed minus 8x squared plus 24x minus 16 is 0. Now by rational root theorem, let's just guess divisors of 16 plus or minus. 1 will not work, that'll give us -1. 2 gives us 16, minus 16 is 0. 4, -32, -16, -48 plus 48 is 0. So x equals 2 works. So x minus 2 is the factor of this. If we do the long division, we should get this. So this is x minus 2, and then if we check rational roots of this, we see that 2 works, right? Yeah, 2 works. So x minus 2, and then we get x squared minus 2x squared plus 2x minus. Well, that's not right. X cubed minus 2x squared plus 2x minus 4, right? So the final product is this equation over here, which is a nice equation. And then we want to find the sum of the x coordinates of the distinct points. So x equals 2 will be a distinct point. No need to repeat it since we're given distinct. And then over here, let's just make sure that x is actually going to be a real number. We don't want to sum up imaginary points because they don't exist. Discriminant over here is positive indeed. I think it's 20. So by Vieta's, if you sum up these values, you get -2. So 2 plus -2, sum of the values of x is 0. Okay, question 7. Let x be a positive real number. Find the maximum. Okay, that's funny. Number. Find the maximum possible value of this. Okay, so first of all, we could try calculus, right? We could set the derivative equal to 0, solve for critical values, but we don't really want to do that. The derivative gets really ugly. Just looking at it right now, if you were to differentiate the top, you get like 2x minus 4x cubed over 2 root x to the power 4 plus 4. That'd be really ugly to deal with. I tried it myself and I didn't make much progress. So that was my first approach, didn't work. The second approach was to try a trig substitution, mainly like hope that x equals √2 tangent theta, where theta is between 0 and pi over 2 would work, because if you do x to the power 4 plus 4, you actually get a nice value. I believe that'd be for 2 secant theta. But this, again, you'd have to do some nasty differentiation. That doesn't really work out. So let's take what we learned from question number 4, I believe, which was the one with the floor functions, and let's try to use the AMGM inequality. We're given an inequality, and we're given that x is a positive real number. So in fact, we need to use the AMGM inequality to do this. How? So x squared plus 2 minus root x to the power 4 plus 4 over x. So we have a radical. For common algebra wisdom tells us to multiply by a conjugate. Doing so gives us x squared plus 2 squared, and then cancel minus x to the power 4 plus 4 over x, and then x squared plus 2 plus root x to the power 4 plus 4. X to the power, these cancel, so we're left with 4x squared over x squared plus 2 plus root x to the power 4 plus 4. Nice. X's can cancel. X is obviously not equal to 0, so we can safely cancel the x like this. So now we have to maximize this expression over here. Now it's actually, we can employ a clever trick. We really want to use AMG inequality, right? So copying this down, well, let's do this. 1 over x times x squared plus 2 plus root x power 4 plus 4. Motivation for this is if you're to multiply the first two terms, you get x plus 2 over x, which is something convenient in AMGM since the geometric mean is going to be a constant. However, this is even better now because 1 over x is root 1 over x squared. So when distributing it among root x to the power 4 plus 4, you'll get root x squared plus 4 over x squared. So let's just do what I'm saying for x plus 2 over x, maybe group this, and then plus root x squared plus 4 over x squared. And now it suffices to maximize this. In other words, it suffices to minimize this. Minimizing this would in turn maximize 4 over that. Let's do AMGM now. So x plus 2 over x is greater than or equal to 2 root 2. Equality case of AMGM is when all the AIs are equal. So x equals 2 over x would be equality case. So x equals root 2 since x is positive. And then x squared plus 4 over x squared is going to be greater than or equal to 4. Equality case is when x squared is equal to 4 over x squared, or in other words, x equals root 2 again. So when x equals root 2, we actually minimize x plus 2 over x and root x squared plus 4 over x squared. So plugging in x equals 2, root 2 would in turn maximize this expression. So let's do that. 4 over, well, I guess what I'm going to do is I'm just going to plug it into this first. I like this one the best. So 4 root 2 over 2 plus 2. X to the power 4 would be 4 plus 4 is 8. Take the square root, you get 2 root 2. So this is 4 root 2 over 4 plus 2 root 2. So simplified, 2 plus root 2 multiplied by a conjugate. This gives us, I believe, 4, 2, 2, root 2, 2 minus root 2. So 2 root 2 minus 2. So this should be the answer. Okay, let's move on to the next problem. So now we're given this kind of thing, n over n to the fourth plus n squared plus 1. First thing you need to realize is that this denominator is, this denominator is actually factorizable. N to the power 4 plus n squared plus 1 is n to the power 4 plus 2n squared plus 1 minus n squared. This is a perfect square, n squared plus 1 squared, and then this is n squared. So n squared plus n plus 1, n squared minus n plus 1. Okay, so now we actually want to make this kind of telescope, because we actually see if the denominator is factorizable 99.9% of the time in a contest setting, it'll be a telescoping series. So if we were to, I'll call this A and I'll call this B. If we were to do A plus B, we get 2n squared. Yeah, we get 2n squared plus 2. 2n squared plus 2 does not really direct to n relate to our numerator n in any nice way. However, if we subtract, if we do A minus B, we get 2n. 2n is very closely related to n, you just take a half of that. So in turn, this is summation n equals 0, infinity, half of n squared plus n plus 1 minus n squared minus n plus 1 over n squared n1 n squared n1. Great. So now 1/2. So we have a constant factor of 1/2 and we're summing over all the place. We can just take that 1/2 off the summand. So this becomes 1/2 summation n equals 0 to infinity. And then now let's just divide this like we'd normally do for fractions. This would be 1 over n squared minus n plus 1 minus 1 over n squared plus n plus 1, if I remember correctly. Indeed. So let's just experiment with this a little bit. It'll for sure telescope. Let's just see. Plugging in n equals 0, we get 1 over 1 minus 1 over 1. Plugging in n equals 1, we get 1 over 1 minus 1 over 3. Plugging in n equals 2, we get 1 over 3 minus but I was plugging 2, right? Okay, 2, 1 over 7. If I plug in n equals 3, I get 1 over 7 minus 1 over 13, etc. In turn, boom, 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 boom. This will keep on going up to infinity until we get such a negligibly small number, it won't even matter. This cancels. So in essence, all we're left with is 1/2 times 1, which is 1/2. Okay, number 9. This was an interesting one. I've actually seen competition problems like this before, so it's good to know the general idea. So this number has exactly 4 prime factors and we want to find their sum. So 27 million, is that the 1/700,000? Yeah, 27 million one is nothing but 27 million. So now what we can do is let's prime factorize 27 million. 27 million is nothing but 1 million times 27, so 3 cubed, which is 27 times 10 to the power 6 plus 1. Now what I'm going to do is I'm going to let x equal 10. I mean, let n equal 10. So we have 27 n to the power 6 plus 1. Now, actually, n equals 10, it took quite a bit of experimentation. Essentially, what we want to do is, obviously, we want to factor this object. For example, let n be any general number, and we want to factorize it further. For example, if you let n equal 3 times 2 squared, 3 times 10 squared, this object will become n cubed plus 1, which you can use difference of squares. Ultimately, what you want to do is you want to choose an n such that even when you factor this into a quadratic, okay. We can actually factor the quadratic further. In this case, n squared minus n plus 1 is not factorizable in the integers. So if you choose n equals 10, this actually works. We can actually factorize this in integer. We can actually factorize 27 n to the power 6 plus 1 into integer polynomials. So 3 and n to 6 plus 1, right? This is essentially this. So 3n squared, this can be factored as the following: 9 and 4 minus 3n squared plus 1. So it can be factorized as follows. And then now look at this: 3n squared. If I do 3n squared minus 1 squared, I get minus 6n squared plus 1. Minus 6n squared, to get minus 3n squared, I'd have to add 3n squared. Not factorizable. You'd have to, that's not a perfect square, which is not good. However, if I do plus 1, If I do plus 1, I get 9n to the power 4 plus 6n squared plus 1. So I can subtract 9n squared. And now this is amazing. This is factorizable. We've factored this 3n squared plus 1, 3n squared. This is basically 3n squared. This is 3n the whole square. So 3n squared plus 3n plus 1, 3n squared minus 3n plus 1 with n equals 10. So now let's write this. 3n squared plus 100 would be 301. If you plug in n equals 10, you get 331. And if you plug in n equals 10 here, we get 271. So we're saying, so basically they're saying that this has 4 prime factors. Let's first check 301. Not divisible by 2 because it's not odd. I mean, not even. Not 3 because it doesn't sum to a multiple of 3. Not 5. 7 does work. So 301 divided by 7, if you do long division, 43 times 7 times 331 times 271. Now we need not check further. We're given in the problem that this can be expressed as 4 primes. So these must be primes. So the answer is 50 plus 331 plus 271. And if you do the arithmetic, you get 652. All right, last problem. Find the sum of the absolute values of the roots of this. So first thing you want to notice is x to the fourth minus 4x cubed. I'm already thinking about this. Right? This, you see these two coefficients in the binomial expansion of x minus 1 to the power of 4. This is x to the power of 4 minus 4x cubed plus 6x squared minus 4x plus 1. So just how far off are we? So let's see. Forgot the x squared. Okay, interesting. Minus 4x squared plus 16x minus 8. This is x minus 1 to the power of 4. Now, I have a negative 4x squared in my desired expression, but I have a 6x squared here. I'd have to subtract 10x squared. I have a negative 4x over here. I want to get to 16x. I'd have to add 20x. I have a 1 here. I want to get to negative 8, so I'd have to subtract 9. And this is equal to 0. We want to find the roots of this. So x minus 1 is equal to 10x squared minus 20x plus 9. And then let's difference. I mean, let's complete the square. If I do 10x squared minus 1, I get 10x squared minus 20x plus 10. I'd have to subtract 1. And now look at this. X minus 1 power 4, x minus 1 squared plus 1 equals 0. This is basically can be converted into a quadratic expression if we substitute, maybe, for example, t is equal to x minus 1 squared. In that case, we have t squared minus 10t plus 1 is equal to 0. Quickly use the quadratic formula. T is equal to 10 plus or minus square root of 96. 96 would be 4 root 6 over 2, which is basically 5 plus or minus 2 root 6. Okay. So case 1 is when t is equal to 5 plus 2 root 6. In that case, we have x minus 1 squared is equal x minus 1 squared is equal to 5 plus 2 root 6. So let's solve this case individually. So x minus 1 is the plus or minus the square root of 5 plus 2 root 6. Now, what we can do is we could easily guess this, but we could write root a plus root b is equal to root 5 plus 2 root 6. Now squaring both sides, we get a plus b plus root 4ab is equal to 5 plus root 24. So a plus b is 5 and ab is equal to 6. So by Vieta's, a and b are the roots of a polynomial q squared minus 5q plus 6. So a is equal to 3, b equals 2, and any permutation of that. So x minus 1 is equal to plus or minus root 3 plus root 2. So x is equal to 1 plus or minus root 3 plus root 2. And then the problem asks us to find the sum of the absolute values. So our first one would be maybe 1 plus root 3 plus root 2. And then 1 minus root 3 minus root 2 is also a root, but this is a clearly negative root. So taking the absolute value would be -1 plus √3 plus √2. So x1, x2 equals. Okay, first case, we get these roots. Case 2. Oh man, I cannot. Okay, x minus 1 squared is equal to 5 minus 2 √6. Easy to check, easy to guess and check that x minus 1 would then be plus or minus √3 minus √2. Yeah, so x3 would then be, so we could have √3 minus √2 plus 1. That's perfectly valid. That's positive. No need to take any absolute value. Or we could have x minus 1 is the negative representation of this, √2 minus √3. So x is equal to √2 minus √3 plus 1. Now that is a positive number. So no need to take any absolute value. So summing all this, I essentially, if I sum x1 and x2, I get I get 2 √3 plus 2 √2. And if I sum x3 and x4, these cancel and I get 2. So this, and that's our final answer. So thank you for watching this video. If you want, I can do more HMMT problems in the future, maybe from more recent years. Make sure to subscribe, and thank you for watching.